Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. In this session, we are going to talk about a very important topic: how to properly analyze the output of simulations. Before we get to this phase, we have to do a lot of hard work. We have to properly approximate a model that captures the reality of the system that we want to model. And then we have to code it. We have to go through the phase of validation and verification. And then we have to properly design what kind of experiments we are going to run on this simulation model. Only then will we be able to get output from this simulation model. The important thing is that we do not let all this work go to waste by making mistakes in the part of output analysis. Unfortunately, most simulation studies fail in this aspect, and this is because once a simulation experiment is run on a system, you would get some output. It must be remembered that this output is not the answer. It's just a random variable that can only give you some indication of the true output parameter. So on the slide you can see that you have a simulation model, and input distributions are fed into the simulation model as input. And these input distributions are known because we model them ourselves. This is just an approximation of reality. Then from the simulation model, you get output values. It must be remembered, and I emphasize, this must be remembered, that simulation output is random. If you were to repeat the experiment, it is possible that you will get a different answer. It is also possible that you would get a very different answer depending on the output distribution. So it's important that we not only get the precise value of the parameter that we want, the point estimator, but also we estimate what kind of variance is there in the output distribution. If we were to do the same experiment again, how wide do we expect the answer to be from the current answer that we have? So this is the focus of today's session, and let me outline the course of this session. The first thing I'm going to talk about is the basis of output models and analysis. We're going to talk of confidence intervals, of estimation, and we are going to see what role statistics plays in proper analysis of simulation. Secondly, we're going to talk about analysis of terminating simulations. In previous sessions, we've seen that we mainly have two kinds of simulations. In terminating simulations, we have some event or some time that marks the natural end of our simulation. So we have a predefined end of the simulation. But in steady state simulation, we're not interested in transient simulations, but we want to let the system work on for a long time and see what value does the output stabilizes on. And that is known as the steady state parameter of that system. In steady state simulations, we're interested in finding the steady state parameters. So the analysis part also differs. In general, it is easier to analyze transient simulations because in steady state simulations, we have to cater to additional issues like the initial transient problem. We also have to see how long we have to run the simulation, which is not a problem in terminating simulations, because in that case, we are already given how long the simulation is going to run. So let's start by reviewing some of the things that we've already covered about estimation and about statistics. So I encourage you to go back and see our earlier sessions on sampling, on confidence intervals, so that you get a clearer picture of what we're going to talk about. But for being self-consistent, I'm just going to talk about these things in some detail, but not in as much detail as we've already covered. So the first thing is that when we have simulation output, we can envision that output in different contexts. So the first model that we have of the simulation is the IID model. In other words, we're going to get some output from the simulation. We can imagine that all of these outputs are independent and identically distributed. At the very outset, let me tell you that this is a very wrong assumption. Especially in simulations that are dynamic, most of the random variables would be autocorrelated in the sense that the random variables that are temporally co-located are going to have some dependence. But we are going to talk about this so that we can highlight the dangers in making this assumption. It must also be highlighted that the statistics that we covered at the start of this course, the method of confidence intervals, assumes that we have IID random variables. So when we want to extend those results to simulation studies, we have to carefully see where the result applies and where it does not. Generally speaking, we want to convert simulation output into IID random variables so that we can then analyze it using statistical techniques, the classic statistical techniques. So before we get to that, let me just revise some of the things we've already done. On the screen now, you can see a simulated model, normal IID model, and we are creating some samples of this. So if we have normal IID data, you expect that there would be no pattern in data because there is no dependence between successive random variables. You can clearly see that most simulation output that you get is not going to be like this. So IID is not a very good model of simulation output, but it has a very strong theoretical basis of analysis. So what we're going to do is we're going to convert our simulation output into IID random variables and then analyze them using the kind of techniques that we are going to shortly cover. So firstly, what is the IID process model? In IID, the first I stands for independent. The second I, followed by D, stands for identically distributed. In other words, all the random variables are independent from each other and they have the same marginal distribution. So things are very easy. You just need to specify the marginal distribution of one random variable and that defines the entire process. So imagine a hypothetical population of observations. You can imagine this as a bag that has the entire observations that can output from this process that you are working on. And it can be described by a theoretical distribution. That is seen on the left-hand side of the slide. You can see a distribution there. And at the center of the distribution is the central value, the mean value specified by mu, because this is a population parameter. When we are working with an IID model, we are assuming that for every random variable, it is defined by the same distribution. So when we have that, then successive observations would differ somewhat because they are drawn according to a distribution, but then they would be coming according to this distribution. And you see certain observations shown on the right half of the slide. And on the basis of that, we can derive a sample average. And this X bar is an estimate of the population mean. This is very important because in simulation, the output that we are getting is just a random variable drawn from some unknown distribution. So from these random variables, we cannot solve or give the right answer. We can only estimate what is the right answer, what is the population parameter. So therefore, I encourage you to again revisit the relevant sessions. Now we can move forward and see how we can actually do the estimation. So what we actually have is just the sample. On the basis of that sample, we want to derive information about population parameters. So why would this work? This actually works because of some strong properties on the basis of which estimation theory works. The first property is known as the law of large numbers. In other words, if you draw a large enough sample, the sample mean is going to converge towards the population parameter. This is very important because this lets us estimate the true parameter on the basis of the sample alone. And it's important that for IID random variables, the sample mean is an unbiased estimator of the population mean. In other words, the expected value of x bar is the same as mu. So if you were to take a long enough sample, and if you were to do this many times, then there is no bias. You would have the same value as the population parameter. So all is fine here, but the assumption is of IID random variables. We call sample mean as the point estimator of the population mean, because it is just telling us what the value is. It's not telling us how precise this information is. It must be pointed that the sample mean is a random variable. You do this experiment again, chances are you will not have the same value. It will be from the same distribution, but the values would differ. So also x bar, the sample mean, is going to differ from sample to sample. So we need to also describe the preciseness of this x bar, and we do this by specifying a sampling distribution. We also note that sample variance can also be used as a point estimator of the true population variance. So we have a sample. On the basis of that, we are inferring about the population. The variance of the sample can be considered as a point estimate of the variance of the population if the sample is large enough. And for IID random variables, the sample variance defined as shown on the slide, it actually is an unbiased estimator of the population variance. In other words, the expected value of S square is the same as sigma square. So that is good. Again, this only holds in IID random variables. What is the implication of this for our simulation studies? It's important because we are going to need information about how precise our estimate of the sample mean is. In other words, the sample mean is going to have a sampling distribution. X bar is going to have a distribution, and we can imagine that if we keep on taking samples, the sample means are going to be distributed as per the sampling distribution. Obviously, we require, or we would prefer, a very precise distribution in which the sample means do not vary a lot. And therefore, on that basis, we can infer with confidence. But it turns out that due to central limit theorem, we can talk about the standard deviation of the sampling distribution, which is known as the standard error. The standard error is a function of the size of the sample. If you increase the size of the sample, the width of sampling distribution is going to become more narrow and narrow. And the key aspect for which I highlighted the fact that sample variance is an unbiased point estimator of the population variance is that we don't know population variance in advance. When we are doing network performance evaluation studies through simulations, when we are getting output, the output distribution, the true output distribution, is unknown to us. So whatever estimation we are going to make is only going to be on the basis of whatever statistics we can calculate on the sample. And it turns out that sample variance is an unbiased estimator. That's good for us. And from this basis, we can then derive the estimate about the preciseness of our point estimator. And the method for doing that is the method of confidence intervals. Let me just recap the most important points. So we see on the slide a population distribution. We are imagining that the population is normally distributed with mean value of mu and with a standard deviation of sigma. This is an assumption. It certainly does not have to be true for all the cases that your population distribution has to be normally distributed. We are going to show it because it's easier to understand. So if you have this distribution and you are going to take samples from this, the sample mean is going to have some sampling distribution, and that is shown on the slide. This thing is again a normal distribution, and its central value is mu, and the standard deviation is sigma over under root of n. And it's worth emphasizing this point. The center of the sampling distribution is the same as the center of the population distribution. In other words, the expected value of both these distributions is going to be the same. The sampling distribution has less variance than the population distribution because we're working with averages. And it is less by this factor. We note that the sampling distribution is sigma over under root n. So the more the size of the sample, narrower would be the sampling distribution. From this, we can form an interval estimate. And the interval estimate is the region around the point estimator where we expect the true parameter to be. So we can also refer to this as the confidence interval half width. So you can see that on the slide, the point estimator is shown by the cross, and the one part of it towards one side, you can see 1/2 width of the confidence interval. The entire confidence interval would be composed of both the half widths. So on the basis of this information, we see that the standard error is equal to sigma over under root n. Imagine that we take a sample of some size. On the basis of that, if we were to know sigma, we could calculate the standard error of the sample mean. On the basis of that, we can calculate the confidence interval. Let's imagine we take a sample and we calculate this confidence interval. You can see a cross and 2 half widths on the bottom of the slide. We see that this interval does contain the true population parameter. The point estimator is a little off the true parameter, but the actual population mean is contained in the entire interval. Let's do another sample. So we see that again, the sample mean is not the same as the population mean, because our samples are of finite size and there is some random variation which is precisely captured by the sampling distribution. So the red curve that you see is the sampling distribution. The sample mean is going to be distributed according to this distribution. But still, because we have specified the confidence interval, we know the preciseness of our point estimator, and therefore even this interval estimate has the population parameter. We do this again. Now we are very close to the population parameter just by chance. And obviously because we are close, the interval contains the true population mean. Let's do this again. It again contains the true population mean. But now, just for illustrative purposes, I have shown an interval which is too much in the tails of the sampling distribution. The point estimator is far off from the true parameter, and the interval estimate does not contain the true population parameter. This will happen because when we say we have a 95% confidence interval, we are only catering for 95% of number of trials. If we do a lot of trials, let's say we do 100 trials and we calculate 100 intervals, then approximately 5 of them would miss, because that is the confidence level we are working on. If we were to choose a very large confidence level, then our interval would be large as well. The important thing as it relates to simulation is that in simulations, both mu and sigma are generally unknown, and therefore we cannot straight away use the standard error formula of x bar, which is equal to sigma over under root n. We need to estimate sigma from the sample itself, and for that you might recall we had a discussion in earlier sessions. We see that the distribution of the sampling distribution is actually a function of different things. It is a function of the size of the sample. If the sample is large enough, your sampling distribution is going to become approximately normal. Even if you are estimating the population variance, you are plugging in the value of the sample variance in place of the population variance, but because your sample is large, this is a good approximation. And the sampling distribution, when you have a large sample, can be approximated either by the z distribution or the t distribution. But when you have small sample, then it must be the case that your original random variables must be normal IID random variables. Only then can we analyze using the standard methods of confidence intervals. So if the true population distribution is normally distributed, and even if you don't know the population variance, you can plug in the value of s square in place of sigma square, and calculate the confidence interval. But now you must use the t-distribution because of the fact that you have less number of observations. When you have small number of observations in your sample and your original population is not normal, then we cannot make use of the standard confidence interval methods because we don't know precisely what the sampling distribution is. So in summary, the interval estimate is equal to x bar plus the margin of error. And it's very important that we specify and calculate the margin of error. If the margin of error is high, then our point estimator is not of great value. But if the margin of error is very low, then the point estimator has a lot of value. So the confidence interval half width is calculated as per the formula shown on the slide. The half width represented by h is equal to t hysteric multiplied by s over under root n. We are making use of s in place of sigma. And because of that, we are also making use of t statistic. We are making use of the t distribution. The t distribution for a large sample becomes like the normal distribution itself. So we must almost always use the t distribution because it captures the issues related to small samples. Now we can talk of non-IID output models. But we make a concession. We're not going to talk of completely arbitrary distributed output models. We're going to talk of identically distributed models, but those that have dependence. In IID random variable model, we were using independent and identically distributed random variables. But here we are using identical distribution for every random variable, but they may be dependent. And this is an accurate enough model of network simulations. So you can see on the slide two graphs. The graph on the left hand side is a simulation from a normal, identically distributed, positively dependent data. So you have some identical distribution that is consistent throughout time. But then you also have some dependence. You see that on the left hand side graph, closer values are closer together. It's not like the graph we saw earlier for the IID random variables. On the other side, you see simulations from normal, identically distributed, negatively dependent data. In such cases, the successive values are going to be on the opposite sides of the average value on average. So these are some kinds of dependence. We stress that we are going to focus on identically distributed models. And this is primarily for tractability, and this applies when the simulation results have entered the steady state. In the steady state, we can envision that successive random variables have the same distribution. But during the initial stage, successive random variables may have completely different distributions. Imagine that you have a queuing system. The first customer is not going to have any waiting, assuming that the queuing was earlier starting in an empty idle fashion. The servers are idle and the queues are empty. But when we get into the steady state, successive customers are going to see similar distributions of waiting time. That is what is meant here, that if we get into the steady state, then the distributions can be envisioned to be identically distributed. But it must be remembered that this is primarily an approximation. It allows us to analyze simulation output, because if we don't assume identically distributed random variables, then we need to specify what is the distribution of every random variable separately, which is clearly a very demanding task. The main model that we use for non-IID output model of the simulation is the covariance stationary model. In a covariance stationary model, we're not assuming that the successive random variables are independent. But what we are assuming is that the mean of the model remains the same across time. Also, the variance remains the same. And lastly, the autocovariance remains the same, and it is only a function of the distance between the random variables. If we want to see what is the autocovariation between random variable at this time and which is following after it, because autocovariance is defined as the dependence between the expected values of these random variables, it would remain the same if we were to think of this at a later time for the same lag. In other words, we can say that the autocovariance does not depend on what time we are considering, but the autocovariance of two random variables only depends on what is the relative distance between these two random variables. This relative distance is also known as the lag between these two random variables. So in summary, you would say that in a covariance stationary process, the mean and autocovariance at different lags do not depend on time. We note here that variance is just a special case of autocovariance. And when I say autocovariance, it actually means the variance between one random variable and another random variable that belongs to the same process, but that random variable is some distance away. So in a covariant stationary process, we are making these assumptions, and this would hold when the simulation is in its stationary phase, when it gets into the steady state. Before it gets to the steady state, we have some transient period. And during that transient period, the distribution of successive random variables would be continuously changing. And this is one of the main challenge in analyzing simulation output, that we have to identify the transient period and then maybe discard that data, because we only want to analyze the steady state results if we are considering steady state simulations. In transient simulations, we do not worry about that, because it is an explicit consideration that where are we starting from and how long we are going to do a simulation. So in that kind of simulation, we must take into account the transient features. So the important thing that arises here is that while we have identically distributed random variables, you have some autocorrelation, and the effect of autocorrelation on network performance is quite significant. I must point out that if S square is less than the population variance, which would be the case when we have positively related data. In other words, when you have positively autocorrelated data, things that are close together, random variables, are going to be alike. And if you just measure a finite period of observations, you would not be able to estimate complete variation in the process. And therefore, your estimate would be skewed such that you are thinking that your estimate is very precise, but in actuality, you would see that your estimate may be far off. So this then is one of the drawbacks. This is the main reason we say that you should not be using the IID model for simulation studies. And that is highlighted here, because simulation studies are clearly not IID. They may be approximated by covariant stationary processes, and if you do that, you would see that the results that you have are going to underestimate the real variance. And because confidence intervals are based on the estimate of variances, the confidence intervals are also going to be inaccurate. And therefore, we must properly take into account the dependence in the output of simulation. So I can now tell you in summarized form what are the main problems that make estimation of network performance evaluation simulation output difficult. The first thing is the presence of autocorrelation. When we are making a sample run, the successive random variables are dependent. And we've also seen that in internet traffic, you have large dependencies, long-range dependence, and the autocorrelation function hyperbolically decays. In other words, whatever happens now is going to have an impact on random variables that are going to come much later. So because of that, this is problematic. The second important aspect is the presence of heavy-tailed input. Because if you have a lot of variance in the input model, the output model is also going to have a lot of variance. One practical consequence of this is that it takes a very, very long time for the simulation output to reach the steady state. So you would be in transient state for most of the time, and when you are in the transient state, the distributions have not converged to the steady state distribution, and any estimation done in the initial transient phase will not be an accurate depiction of what would be the true parameter that is going to manifest itself in the steady state. Lastly, related to this is the initial non-stationary period, because successive random variables at the start of the simulation are going to have different distributions. And the reason for that is that we typically do not know how to start the simulation. Because if we were to start the simulation in the steady state conditions, then the initial transient would not be a problem. But when we are doing queuing analysis, typically we start in an empty idle state. The servers are idle and the queues are empty. And this is clearly not optimal. If we were to do this in a networking context and imagine that all the routers have empty queues, that will never be the case. On the internet, you always have some load. And because of that, the simulation is going to take some time to get to the steady state. Any measurements during that state is going to bias your results. So these are three aspects of network performance evaluation simulations that make the task of estimation very difficult. Let me now explain these one by one. The first aspect is the aspect of dependence. So in an earlier session on measurements, we saw how dependence in measurements can create problems. Because when you have dependent measurements, the information that they provide is limited. Imagine a student taking one real measurement and then copying 40 other observations that are somewhat above and below this value. Clearly, this is not going to be very informative. But then the real reason this is not informative is that all the measurements are dependent. So in effect, you only have a single measurement, and all the other measurements are related to this. So we need to ensure that the measurements are independent from other measurements. And a similar case would apply to the case when you do analysis to determine the average delay based on trace route or ping in one session. Whatever you're going to find is going to depend on what were the network conditions at that time. Also, you can imagine the third example is of going to an election office of some political force, and then you're going to sample people there. Chances are that you would have similar results. And these are all examples of dependent measurements, and I hope the point has been made that dependent measurements decrease the value of information that we get. The second key aspect that was mentioned was the heavy-tailed impact. Let me show you 10,000 synthetic observations created from Pareto distribution, which is the signature heavy-tailed distribution, and we are choosing alpha value of 1.2 and a mean of 6. So when Pareto distribution has alpha value less than 1, it does not have a well-defined mean. But in this case, we have a well-defined mean, but the importance of Pareto distribution is that it captures the extreme events. If you observe that most of the observations are around 6, but then you have some very extreme observations that are maybe 2 or 3 orders away from the central value. If you have such an input, the output is always going to be transient. And whenever such extreme events happen, your sample mean is going to take a big plunge. And because of that, we would always be in a transient state. Sometimes, for certain Pareto distributions, you will never get a convergent mean because simply a mean does not exist then. You would have continuously increasing values at the simulation output. So how do we deal with this? Some approaches have been proposed. One approach is to use bounded Pareto distribution, because a Pareto distribution is unbounded. If you were to do this for a very long time, you are going to have very, very large extreme values, which may not be possible in a physical sense. So you can put a bound on the upper value that you can expect. Also, as a practical consideration, we can use the log normal distribution, which has a tail that is heavier than the exponential distribution, but less so than the heavy tail distribution like Pareto instead. And using that, we can have a pretty good approximation of real network data. And the third thing is that we should always analyze simulations that require heavy-tailed input workloads as transient, because the statistics are always going to change. The third aspect of non-stationary output of simulations can be seen from the slide, and we are going to see how the initial distributions are not the same as the distribution we have in the steady state. We are given a steady state mean value, and that is shown on the slide. You see that the expected value of the initial random variables is far below the steady state mean value. You can also start in conditions where the expected value is far above the mean value. The important point is that the initial conditions typically have an impact. You see that the distribution is changing, and it is only when we get to the steady state that we have identically distributed approximations, that successive random variables are going to have a distribution that is approximately identically distributed. So from this we can note that the initial period must be addressed. Otherwise, any readings that are made only from the transient period, or any observation that includes measurements made in the initial transient period, are going to misestimate the real steady state value. Okay, so now before we get down to actual techniques, I can now tell you some strategies that we will be using for analyzing simulation output. The first thing is that we will still be using statistical techniques that have been developed for IID random variables, but not directly. For both transient simulations and for steady state simulations, we'd be transforming the random variables that we have from there into IID random variables, and then we would be using these techniques. And also we must be handling the non-stationarity and the autocorrelation part very seriously, otherwise our results are going to be wrong. Let's now talk about terminating simulation analysis. In such simulations, the parameters have to be estimated as defined relative to specific initial and stopping conditions that are intrinsic part of the model itself. In other words, we don't have to worry about when are we going to end the simulation, because that is part of the model. We have a natural time by which we will be stopping this simulation. It will either be a time, a fixed time, or some event that will happen. Generally, we want to choose conditions, the initial conditions that are representative of the system that we want to simulate. And therefore, we include the transient period in the analysis of transient simulations, or in the analysis of terminating simulations. So the key aspect here is that while one simulation run gives us autocorrelated value, if we were to do replications of this experiment again and again, we are going to have IID random variables. In other words, in a single replication, we have dependence. So we do not consider successive random variables from the same replication. We consider one sample run or one replication as a single observation. But we perform many different simulation runs, and we make use of observations one at a time from a replication as our sequence of IID random variables. And once we have that, we can make use of statistical techniques that are developed for IID random variables to form a point estimator, to form an interval estimator, and to derive the confidence interval. Let me show you an example. We see that inside one replication, we are going to get values, for example, y11, y12, all the way till y1m, where the first one in the subscript in y11 tells us that this is the first replication, and the second part is the number of observation in that replication. So y1m is the mth observation in the first replication. Clearly, within replication, the data is autocorrelated. So we make use all of this sequence in the first simulation run, and we derive some statistic on the basis of that, typically the average value, and we now treat this as a new random variable. We do the same for all the other replications, and then we have a sequence of IID random variables. The key aspect here is that the replications are done so that the sample runs are independent. That means while the starting conditions are going to be the same, but we're going to use different random numbers. We're going to assume that the randomness driving the simulation is different, and therefore it is a valid assumption that successive across replication data would be IID. And now we have this data, and that is shown as y bar of 1 dot, which means that y1 dot tells us that this deals with observations in the first replication, and the bar tells us that this is an average over the observation in the first replication. We do this for all the R replications, and then we can make use of the sample average as the point estimator of mu. We can make use of sample variance as the point estimator of the population variance. And then from there, we can also calculate the confidence interval. So this then is quite straightforward, and the analysis of terminating simulations is simpler than the analysis of steady state simulations, because we only need to think about how many replications we want. We don't have to worry about the initial transient period, and we don't have to worry about how long the simulation has to be run. So regarding the question that how many replications are needed, that depends on when we actually get to a precise enough value. So as an example of that, we are going to demonstrate two techniques. The first technique is the graphical method technique. So we obviously want a lot of replications, because that is going to give us a better estimation of the true population parameter. So on the slide you can see data for 20 different replications, and then we also see the cumulative mean for that. And when we draw that, because the cumulative mean has the property of averaging, we see that the cumulative mean settles into some steady state. And we see that heuristically speaking, it is after 4 replications that we are settling into a steady state. It must be pointed out that steady state refers to the distribution, not to the output values. In other words, the output values are not going to be constant. It's just that the pattern they are following, or the distribution they are following, is going to become stationary. The other technique that we can use is the confidence interval method. And using this, we can make use of the formula for calculating the interval estimate, as you can see on the slide. And the right-hand example is actually related to the left-hand example. The data is the same. If we calculate the confidence interval, it makes sense that if you increase the number of replications, the interval width is going to narrow down, because the width is a function of n. You have under root n in the denominator. And therefore, larger replications would actually imply narrower width. So we can actually specify the width that we want, and then we can keep on adding replications until we have reached that level of preciseness. And this is a method known as sequential simulation. You keep on replicating until you have reached the precision that you require about the estimate. Okay, so this completes our discussion on terminating simulations. We can now talk about steady state simulations. The key challenges here are 3. The first challenge is shared with the earlier terminating simulation, in which we have to determine the number of replications that we have to perform. The other 2 challenges are unique to steady state simulation analysis. The first challenge is determining the length of the warm-up period. In other words, what is the initial transient period in which the distributions are non-stationary? And the second main challenge that is unique to steady state simulation analysis is deciding on the length of a replication. Because the larger the length of a replication, the better it would be. But obviously you have practical considerations as well. So we will now be tackling these challenges and telling of some common solutions now. So we start by showing a graph of initial transient. We see that the initial simulation output would be different in general from the steady state output because of the effect of the initial conditions in which we initiate the simulation. So one important aspect then is, how do we go about analyzing for the steady state, because it takes a long time to reach the steady state. We can do it by doing one very large replication, and we can maybe eliminate the initial transient phase and then focus only on the steady state part. But it turns out that there is another way as well, and that is to do a lot of replications and just keep on deleting the initial transient part. We have to see what approach is best for us. So there are two main approaches, and we're going to see examples of both. The first approach is of multiple small runs, and we call this the replication deletion approach. The second approach is doing a large run, and from that, first of all, we're going to delete the initial transient period, and thereafter we're going to transform the data in some sense that the autocorrelated measurements may be considered as IID random variables. So we start with the solution of multiple small runs, the solution of replication deletion. This is maybe an extension of the approach of independent replication that we've just covered. But the major downside of this approach is that we are actually removing a lot of observations, because in every replication you're going to have an initial transient period. So, but the benefit is that this is a very simple approach and it is more intuitive. So let us now see how a warm-up period appears in the analysis of steady-state simulations. So you can clearly see there is a definite transient period at the start of the simulation before the variation becomes more steady, before we say that variation is coming from some stationary distribution. So a very important question is, how do we determine the warm-up period? When do we say the transient period has finished and the steady state period has started? So it turns out that this is more of a subjective question in which we don't have any rigorous answers. Most of it is best effort, and we're going to see a few heuristic techniques. As you can see on this slide, you have M observations in a run. But we cannot use all M observations because some of them, the earlier L observations, came in the initial transient period, where the distributions were not consistent with steady state distribution. And therefore, we have to determine this value of L and truncate or ignore the earlier L number of observations and only keep the latter part of the observations. But we must be careful because there is a delicate balance here. If we were to delete more data than is necessary, then we are unnecessarily increasing the variance of our estimator. In other words, the interval estimate would become larger because we are basing our estimation on lesser number of observations. But if we were to err on the other side, then we would have bias in our data. So it's very important that we choose the value of L precisely. But it turns out that we only have heuristic techniques of doing that. So let's see an example of this. You can see various values for different days being plotted. We want to do different replications because just from one replication, we cannot determine what is the distribution for that particular day. So for every day, let's say we're doing 5 replications, and then we are calculating the mean on the basis of that. And we do that for all of the days, and then we plot it graphically. We see that the mean settles down into a steady state around the 5th day. And after that, there is not a lot of variance, and the variance that we have seems to be consistent. So we can say then that we have reached steady state. But I guess this reflects to you the nature of our calculation. This is heuristic and is subjective, and we may err on the wrong side, and on the basis of that, our observations may be a little off the mark. Now I will be talking about the method of batch means, which requires a single wrong run in which the initial transient period has been truncated. And then to solve the issue of autocorrelated data, we actually make batches of data. And the assumption is that even in autocorrelated data, the dependence dies off when we are checking the autocorrelation between variables that are far off. It is expected that the variable now is going to affect the next variable and a few more variables, but if we choose a batch of appropriate size, then across batches we expect that we will not have any dependence, and therefore these batch means may be considered as IID random variables, and on the basis of that we can again make use of our standard techniques for calculating the point and interval estimates. So the important benefit of this is that we are wasting less amount of data, and typically we would complete our simulations soon. So batch means is also a very important method. So let us now again see this in some depth. We see that there are n number of observations. What we want to do is we want to first of all ensure that we have a covariant stationary model. We only have a covariant stationary model when the mean, variance and the covariance are not dependent on time. So for that we have to delete the initial non-stationary transient period, and once we have deleted that, the rest of data can be divided into batches, and then we calculate batch means for each one of these batches, and on the basis of that we make use of the standard techniques. As mentioned before, some important issues remain, and those issues are how many batches must we have and how large should a batch be. Obviously the answer, the most desirable answer is that both of them should be large, but practical considerations can ask us to take a trade-off between these two, and there are various effects on the estimates when we make this trade-off. So I recommend that you see more details from some standard textbook in which we are talking about simulation output analysis. So I will now be wrapping up this session and talking of the main things we covered today. The first thing I said was that the simulation output is a result of statistical sampling experiment and results in an unknown distribution whose parameters can only be estimated. It cannot be determined exactly by a simulation run for finite amount of time. Secondly, we have two main classes of simulations. For terminating simulations, the analysis is simple. Observations from a single terminating simulation are autocorrelated, but different replications, that is, same starting conditions, but different random numbers are IID. They have a well-defined terminating point, and we can make use of statistical techniques that are developed for analyzing such IID random variables. For steady-state simulations, we saw that the analysis is more difficult because we have to now also cater for the initial transient period, and we have to eliminate the bias that may accrue from including observations from that period. Also, we need to decide how long the simulation has to be run. So I hope this captures the main essence of the challenges of simulation output analysis, and it enables you to analyze output of simulations better. With this, I'd be concluding this session. I'll see you next time, inshallah. Assalamu alaikum.